the screen with you and let me start. So practically everything which we know as a polymer material is a kind of a polymer network. And there are different kinds of these networks. There are simply networks of long molecules which are not connected to each other in any way, but simply, let's say, entangled. This is something like this. I don't want to show you the magazine, but this, I want to show you this. Yes, and this is essentially a kind of a fluid which very slowly reacts at the external action. So there are no physical connection between the molecules. They can move along each other. And if you pull, if you do this experiment, you see that the first thing which happens with this bag, if you pull, if you look between your fingers, is that it's getting transparent or more transparent. This happens because the molecules orient at this place, start to be parallel to each other, which allows for stress relaxation in this system. And essentially the thing flows. And then it tears, it breaks at this place because nothing can prevent for this flow. If you want to prevent for this flowing, so this is the physical connection between the molecules due to entanglement, and the flow is very slow for long molecules. This we will probably discuss shortly next week in maybe a single lecture of the next week. Another lecture of the next week will be the short wrap up of the whole material. If you want to produce something which is real solid, and solid is something which does not flow or does not easily flow, you have to chemically connect the molecules by introducing the crosslinks. And you can have different molecules, you can have different crosslinks. It's interesting what can happen there. And once I was working on different models of such systems with a student of mine, and it was one of my best PhD students at all. And then what happened, he went to the rubber producer, to the Continental. It's a pity because I thought he is a theorist, but you know. So the story of the rubber as the essentially first polymeric solid started with Charlie Goodyear, around mid-80s, and he invented cross-linking via vulcanization. Because if you have this initial product, which was latex, which was the kind of a juice from the trees from South America, it's, to a taste of a theorist, a moderate molecular weight polymer, and it does flow. If you make a ball of it, if you throw the ball on the floor, it bounces. But if you put it and let it lay for a couple of days, it flows. So it's essentially a fluid, an extremely viscous one, essentially a viscoelastic one. It's interesting what this viscoelasticity means, and I will tell you some fairy tales about viscoelasticity in the last lecture. Essentially it's a fluid. And now we're introducing the cross-linking, in which we at random connect different parts of the corresponding molecules so that they cannot easily flow or easily move along each other's contour. So what happens without cross-linking is that you have a spaghetti in a plate of other spaghettis, but if you move on a spaghetti moves relatively easily within this plate. It rotates. It's like a snake. And what you do by cross-linking, you prevent this rotation motion. Now, the theory of rubber elasticity was put, or let's say the simplest variant of the theory of rubber elasticity. Might be oversimplified, but explaining many of properties of realistic rubber elastic materials was put forward by Flory. It's again around 1950 or 53, I think. I don't remember the date, and I didn't put the date here. Starts from the two postulates. First, think how you prepared, or how Charlie Goodyear prepared rubber. He started essentially from a melt, maybe very concentrated solution, but there is no much difference between melts and very concentration solutions. This melt is a fluid, and fluids are hardly compressible. So if you take a fluid and try to compress it, you push from one side, it starts to push in all other sides. So what you see, what you assume is that you fully neglect the compressibility, and you say that the total volume of your system is practically constant. Now, another thing which lays in the, let me take my iPad, which lays in the core of the Flory's approximation or Flory's theory of rubber elasticity is the fact that the chains in rubber are ideal. Now, why are the chains in the melt ideal? Just let me draw a picture. Just first, let me charge the thing. I'm sorry that it happened today like it happened. So here, now let me start Zoom. Just a second. Give me a minute. Okay, then let me do the following. Let me use our old-fashioned modus, which is drawing on a whiteboard. Just a second. So here I am, and let me draw something. Let me stop this for a second and draw something. Just a second, speaker. Because I also want to see myself whether you can see something later on. In a solution in an athermal solvent, a thermic solvent, a polymer molecule is swollen, and we explained this in a simple term. It's an explanation, it's not the calculation, or it's not something which you can where you can start a physical theory from, but we said there is the so to say, there are solvent molecules, and this thing is like a bag of monomers. Yes, and in the bag you have monomers, and they exert osmotic pressure on the bag, which means that the bag gets larger, the chain gets swollen, the chain swells. Now, if you have, instead of a single chain, the problem is in the osmotic pressure that monomers easily go back and forth through the membrane, so the pressure of the monomers inside and outside is the same. Now, the difference with the polymer melt is, of course, one polymer is absolutely athermal for another polymer. If it is a mono, so to say, if it's not a kind of heterogeneous system, a copolymer or whatever. So you have a chain here, and you have the same chains of exactly the same monomers outside. And this exactly the same means that they are thermal. The Flory hardness parameter is exactly 0 in the model. But now, if you look at this system, if you look, and there are, of course, the chains of other polymers inside the volume occupied by one of them. If you look here at the concentration of monomers as a function of the position, here the center of my specific molecule, which I am considering, was situated, and its concentration, the concentration of these monomers is like this. This is this Gauss, and the concentration of monomers of the other polymers is like this, because they are expelled due to the excluded volume interactions from the place which is occupied by this, but the total concentration, the concentration in the whole fluid, is constant. So these guys are, of course, exerting the osmotic pressure on this bag, trying to make it larger, which leads to swelling. But this deepen the concentration of the others means that from the side of the others there is a pressure, which is an osmotic pressure for other chains. Exactly the same and acting in the opposite direction. So this was the explanation, a qualitative explanation. And then there is no reason to swell. So the chains in the melt are ideal. Now, you know, the explanation is too simplistic, but of course there is a theory by now for this, but there were also experiments. So you can take the chain and have a look at the conformation at the end-to-end distance, at gyration radius, and people have seen they are indeed ideal. When Flory started, nobody believed him, but then people started to believe because they have seen. So two postulates. I have an incompressible fluid made of ideal chains, and then the chains are cross-linked. And now let's have a look what happens in the system. I make an approximation, I make an assumption that the chains are Gaussian and they are phantom. I fully neglect the fact that now I'm considering the chain between the 2 points. There is a chain between the 2 points. I fully neglect the fact that if I have another chain, so the chains interact only in the cross-linking points, and I fully neglect the fact that if the chain meet and cross in a whatever, on a whatever side which is not a cross-linking point, they are interacting. This is neglected. So now I have the subchains. I will consider all of them to be of the same length, which is again an approximation. So the whole theory is very rough, and it's fun that it works so well, essentially. And I consider the excess entropy, which is caused by the deformation of the chains. And I put here, okay, these 3/2, you know, if you want, you can have 3/2 if you have a better theory. It's not 3/2, but let me put 3/2. KBT R squared divided by R0 squared. And here I put simply the same for R0. The only idea here is to have the change in the radius squared. So whenever I pull on the chain, whenever the end-to-end distance is larger than the equilibrium one, the entropy grows. Whenever it is smaller, the entropy grows as well. However, what is interesting here, I only consider the situation when it is larger. First, if it is smaller, the result will not be very different. Second, if I have a fluid, yes, and I push on it, and I assume that my deformation is affine, that each chain is deformed exactly as the system as a whole. This is again an approximation, a very rough approximation. So the whole theory consists of very rough approximations. It's a wonder that it works, but it works wonderfully. So if you push here, it extends in two opposite directions. So on the average, except for extreme cases, the chains are always elongated. So you always pull on them. You cannot essentially push because they are phantom. There is no possibility that they feel any other connections, any other interactions than changing the end-to-end distance. So you cannot really push, but it's okay. Now, these guys, because on the average the chain is symmetric, are all of the order of 1/3 of the mean square distance between the ends. And then I put down from this simple discussion of the excess entropy that if I change the distance between the ends with respect to R0, the entropy grows. I put here the change in the free energy of my subchain. Now, this game with the affine deformation comes in play. So now let me consider I have a piece of rubber. This is essentially a part of the whole piece, which might have a whatever form. But here I have chosen a small piece in which has a shape of a parallelepiped, and deform it, for example, by pulling or pushing it on one side. So if I push it on one side and the volume stays constant, it has to get smaller in two other dimensions. So it elongates, and here it gets smaller. Or if I push, it shortens and gets larger in two normal dimensions. And I assume this affine deformation, which means that if I have a macroscopic piece of this material, all small parts, let's say all small cubes in which I can subdivide the large piece mentally, all these small cubes will deform similarly. Now, due to the symmetry, the deformation in normal directions, the relative deformations, are the same. And now I introduce here these relative deformation factors, lambda x, lambda y, lambda z, which shows by what proportion each of the sides of my parallelepiped or cubus or whatever, or cube or whatever change. And then, since the volume stays unchanged, the product of these guys is unity. Now, due to symmetry, this means that if one, for example, if I pull in z direction, the two other ones, since they are the same, are the square root of this Lx or whatever, if I call this x direction, if I pull in x direction. Now, is this clear? Or do I have to draw pictures, or do I have to explain something else more differently? No.
I have a small
Yes.
question.
Yes.
In the first equation, in the first page,
Yes.
above equation one, why we don't use KBT but just KB?
Where?
But then in
Yeah,
the
because it's
first,
the
in the
entropy.
entropy.
Because it's the entropy. It's
Oh,
in a
right.
thermal system, temperature cannot come in. It simply counts the number of configurations. It's the entropy of a chain, of a single chain with fixed end-to-end distance. And the free energy is minus T delta S.
Yes, yes. Oh, now I understand. Thank you so much.
You're welcome. Now, do you get this? Yes. So
Yes.
wonderful. Yes, wonderful. And now I put this guy here. So I say Rx, Ry, Rz are corresponding lambdas times the unperturbed size, unperturbed distance. And then I collect all the multipliers, and then I say this guy, and this guy are equal, and each of them is equal to R0 squared divided by 3. And this is what I get at the end. So now it's indeed very simple. And I have the change of the free energy per chain under changing its form. And then I say, okay, let me pull in x direction, and let me put here this inverse square roots, and I have the formula for a single chain. Now, how many chains are there on the total? If I look at the picture here, I have a subchain between each two crosslinks. So along the chain, I have here a subchain, here a subchain, and if the chains are long enough, if the polymerization degree within each chain is such that there are many crosslinks within a single chain, I can neglect these ends and simply connect the number of chains with, or the number of subchains with the number of crosslinks, assuming that each crosslink, when I'm going through each chain from the beginning to the end, a crosslink starts a subchain, but it links two chains, which means each crosslink starts two subchains. And another thing which I neglect are the self-loopings, when I have two parts of the same chain connected to each other with a single crosslink. Essentially, I have to disregard them only partly because there are also physical connections. The two loops which might pass through each other still give you a physical connection, which is the true cross-linking, because you cannot separate chains by whatever translation anymore. So essentially, if you want to build a full theory, it's extremely complicated. And I have never went through the full theory, although I know people who did it. But if you want to stay simple, you can stay simple. Now, we can simply say that if you have the concentration of cross links, which is C, the total number of subchains will be 2 times C times V, where V is the volume of your system. Okay, so now let me put everything together, and essentially we are almost at the end of the lecture, which was planned to be short and was even shorter. So this is now my free energy of a system of many subchains. It doesn't matter how many chains were there in the beginning. If you have enough crosslinkers, you have enough subchains to sustain the mechanical stability and the solid properties. And now I put here my square roots, and this is what I get. And then I can pull and obtain the elastic force. Now, how do I obtain the elastic force? The volume is constant, and I essentially can say that d over dx is 1 divided by the unperturbed length times lambda x. And then I differentiate, and then I get the expression. So here, did you get how it works? Or do I have to show? So what I do, I write dx as x d lambda x. X is the length of your system, and lambda is relative elongation, delta x divided by x. So this dx change in the length is exactly this. Now, this guy had a volume in front, and volume divided by x is the cross-section area at the corresponding elongation, essentially. And then I simply differentiate this guy with respect to lambda, and this is what I get. So now I have here the force per unit area, which means it's simply force divided by S. It's something like a pressure. It's essentially a dilatational stress in your system. And this gives you the Young's modulus of your system. And this stress has a dependence on lambda x, which starts linearly and then goes with another slope. So how can I see what happens at large slopes, at large elongations, at small elongations? Very easy. At large elongations, I can neglect this guy. And you simply have the elastic constant, or the Young's modulus, which goes as the concentration of crosslinks, maybe with some prefactor, times kBt. It's an entropic force. It derives from the elasticity of a single ideal polymer, ideal chain. So it has to be proportional to kBt. And then you neglect this guy. Now, what happens at small elongations? You say that your lambda x is close to unity. And then did I put it here? No, not really. Let me show you it in a little bit different manner. So let me first copy the formula. And where is that? Here. I will omit the index x. And now I play with this formula. And I say, now one can see it, and I can control. And I say that lambda is approximately 1. So I say lambda is 1 plus delta. And I'm looking at the linear regime for small elongations. And then I write sigma is equal b kBt 1 plus delta minus 1. And here I have 1 plus delta squared. So what is this guy? I put it as 1 divided by 1 plus 2 times delta plus delta squared. I'm interested in linear behavior because I'm looking for the Hooke's constant of my system. I neglect this, and then I approximate this as 1 minus 2 delta. So then I have here b kBt, and then I have here 1 plus delta minus 1 plus 2 delta. This is kBt, b kBt, and I have here 3 delta. And this 3 delta is essentially, because I remember that delta is lambda minus 1, 3 lambda minus 1. And this is how I come here to this approximate formula. So now this means that for small elongation, I have here the elastic constant or the Young's modulus, or if you want the stress itself, with the slope 3 times b kBt. And here I have the slope 1 time b kBt. So at small elongations, it's harder, then it softens. And then if I go to lambda smaller than unity, then at some instant, this guy will play the major role. Then you have, of course, if you pull, the force acts in one direction. If you push, which means lambda is smaller than unity, the force goes into the opposite direction. And for small lambdas, it gets inverse quadratic. So which means it grows like this, relatively fast. So this red curve is exactly what my expression gives me if I put everything to unity. So now this is the whole theory. Very simple, very nice. And it neglects or disregards as many facts as possible in the case of sorry, but still works, more or less. So if you compare it with experimental curves, what I have drawn here with the dashed blue line, this is not an experimental curve. This is something which I have drawn by hand. So, but what I wanted to tell is that for small and up to moderate elongations, the theory works wonderfully. So what you indeed see is this softening. What you don't see is the behavior for large elongations. So typically they say that if the number of crosslinks is not extreme on both sides, not too few, not too much, the theory works reasonably up to lambdas of the order of 5 to 10. And then it starts breakdown. Now, we will discuss why does it break down at small concentration of crosslinks. This, you know, I will do this tomorrow. And to explain why it breaks down at high concentrations of crosslinkers. This is essentially something which mostly, not only, but mostly, has to do with what we have neglected, namely with the fact that the chains are not phantom. We said that whatever you do with your rubber, the chain elongates, a single chain, on the average elongates. This is true. However, if the chains are phantom, and if the chains are not phantom, this elongation takes place, can take place in different fashions. If your chains are phantom and you pull two of them, they essentially disentangle. They don't feel each other. And the increase in the length of the chain is not as large as when you say that there is indeed a physical interaction here. So essentially, this physical interaction acts as an additional link, which now cannot be released by motion of the parts of the chain. And this means that here on the figure, the effective number of crosslinks starts to grow by the number of these physical entanglements, which you cannot release by, so to say, small moving of the parts of the subchains. And then you come into the regime where you can hardly pull. At the end, anyhow, the chains have finite extensibility, but this comes still in the regime where they are very far from being elongated. This was essentially a very nice and very important piece of theory. And I think you know about polymer materials much more than I do as being a physicist. I mean, not physicist, but a theoretical physicist or even mathematical physicist. And this very simple two-component system with chains and crosslinkers is essentially something which is extremely far from whatever real rubber, except maybe of what is used for making the balloons. Because you have many other components there. But the main mechanism of elasticity is indeed this cross-linking of the ideal polymeric fluid, and it is captured considerably well by this theory, even in this very, very naive, very, very simple variant, which I have shown you here. So maybe this was too short, but I'm not sure. We have to start something new. And moreover, I'm here in my office since 8 o'clock in the morning, and I would like to have a coffee break because I didn't have any coffee break before. But questions. If you have questions, we can discuss. And okay, let me stop this and first ask you whether there are questions to this very short presentation. Are there any? If none, then I will ask you, what is the difference between this simple model and, for example, rubber which you use for the car tires, which is heavy and black?
Car tire rubber has got a lot more different species of polymers and chemicals inside, whereas this is just purely one.
And what is the reason? What is the main component there, essentially? Why they are black? Carbon black. Wonderful. What did you say?
They have a dye in them?
No, it's not a dye. It's essentially one of the main components. Very important there. It's carbon black. It's not used as a dye. It's used for something else. Who knows what for?
It's filler.
If you want to say it's a filler, it's a filler. But why do you need it there? Why do you have to fill something? It has a very important purpose there. And if you wouldn't have to use your brakes, you wouldn't have to put it there at all. And it's not because you make it harder, or not only because you want to make it harder. It's the main component there which is responsible for energy dissipation, for transforming of elastic energy in rubber into heat. And it is quite a complicated stuff by itself because it is fractal. It has a structure in which almost all atoms are sitting on the surface. It's like trees interwoven with the polymer molecules. It's quite an interesting component, and there was quite a lot of works devoted to the structure and properties of carbon black. It's not by chance there, and not simply to make the tires black. It is essentially to improve the energy absorption there, both the heat capacity and the transforming of energy from elastic degrees of freedom or internal degrees of freedom of the rubber into the heat mostly stored in other components and. So a tire is quite or this kind of material is quite a high technological complicated material in which each component has much more meaning than simply bringing it to the corresponding color. Now, you know, I was very fast, I know, but I can give enough homework with what we have. And then, you know, let us have a coffee break for half an hour, and then we go to our tutorial. We will meet again. If there are no other questions, if there are questions, please. If you wonder about something, please. If you want tomorrow, I can give you an infinite, but yes, it will be my last lecture tomorrow. I start early. I can give an infinite lecture of another subject, but tomorrow essentially we will talk only about one problem, and there I can talk infinitely long. If you want, again, I will not be able to present the full theory, but this is part of the theory which I worked myself on, and when I left this kind of theories, there was much development, mostly in mathematics, including two Fields medals, which are the same as Nobel Prize for mathematicians. So there will be something to explain. And I told you already which I wanted. So let me simply introduce something before going for coffee break. I told you if the number of cross-linkers is not too large and not too small. So what happens if the number of cross-linkers is too large? So you see here, yes, that it's an entropic force here, and that the elasticity constant goes proportionally to the number of cross-linkers or subchains or whatever, doesn't matter. So what happens if it is too large?
The material becomes too solid. It's not elastic anymore.
It's
Rigid.
not elastic anymore, it is solid. Now there is, okay. And essentially you used to use it as a solid. You know, you still, they still make expensive pens out of it. It's this solid rubber, or a variant, slightly, so to say, slightly different in composition, ebonite. It was one of the first plastics at all which people used. It's essentially a very good thing, but it's no more elastic. And you can run with the concentration of cross-linkers so high that you also have that the subchains are too short, essentially, to be, for us to be able to describe them as ideal chains. So this is something which is a nice solid, a nice isolator, very inert, and people used it and before they invented nicer and easier, or the plastics which are nicer and easier to process, mostly, because this guy, it's hard to process. You get it solid, and then you have to cut. You cannot form it. You can do nothing. What happens if the number of cross-linkers is too small?
It will be more like latex. It will be more flexible, so we cannot use it either in that.
First, flexible is, what do you call flexible?
Like long chains, like if it require flexibility will increase.
Flexibility will increase because the elastic constants will drop down. We didn't calculate the shear elasticity of the thing, but we could. It's solid, it has shear elasticity. But just imagine you have exactly one cross-linker per chain or less. What happens then? What happens if there are no cross-linkers? I have here another magazine. Now it's a different plastic. It's quite a thick polyethylene. So there are no cross-linkers here. And I pull. I pull slowly, but steadily. What happens here?
We get an irreversible deformation.
You get an irreversible deformation, this is true. But it's different, not very, but still different from the irreversible deformation in a solid. It flows, it's a fluid. Because in a solid, you go into the regime of plasticity, you form, and then it stays in the form. It doesn't flow when the stress decreases below some limit. And here, this guy essentially flows under whatever stress, however, extremely slowly, if the stress is small. This is essentially a fluid or a viscoelastic material. And if the number of cross-linkers gets smaller, you come into a pure fluid regime, practically, where it doesn't have the shear plasticity at all. It does. We will see what happens essentially in a melt. I would like to tell some funny stories about what happens there. But if the number of cross-linkers, imagine you have only one per chain, or less than one per chain, or if you want 1/2 per chain, most of the chains can move easily. And then one can show it mathematically, if you assume that cross-linkers are at random, that most of the chains are either sole, or they form only very small clusters, 1, 2, 3 chains linked. There is no skeleton in the system which can bear the total elastic load. You have a transition, it's a phase transition. It happens at some concentration of cross-linkers. You have a transition between fluid and solid. And this is what I wanted to talk about tomorrow in a very simple setting. Because I will only show some parts of the corresponding mathematical theory without even going into detail for polymeric systems, because they are not quite well investigated. So this is the other thing. So all these solid properties, the elasticity returning back to the unperturbed state if you stop pulling on it, these start above some given concentration of cross-linkers. At this concentration of cross-linkers, something very interesting happens. And very similar phenomena describe also other physical effects in polymer physics on far outside polymer physics, including semiconductors and so on. And this is what I would like to talk a little bit tomorrow. So let's make a coffee break. Now we have 12:30. Let's make it 1. Let's meet at 1. I will only switch off my micro and camera, and I will make some coffee for me, and then we meet again. So see you soon. Bye.